A person rolls a red six-sided die and then rolls a blue six-sided die. Describe the sample space as. Well, this is one way we can describe the sample space. I'm going to make a chart where I write down the outcome of the first die, and we know that that's 1, 2, 3, 4, 5, 6. I'll put that up above here. And then down the side, I'll have the second die. It's not so clear which one should come first, actually. They're both the same. Maybe this is the first die. There's some convention that we list the rows first and then the columns second, but that is really just a little extra. So here we have the first die and then the second die. Then the first die, no, sorry, first die, second die, first die, third die, first die, fourth, first, fifth, 1, 6. So one way or another, we need to get all of them. So we have to have a method to organize our list. Otherwise, we just won't be sure that we get all of them. And this looks a lot like a times table, right? But okay, takes a bit of time. It's doable. And I don't know what to say during this time, except here I am writing this out, and let's see if I can do this, get almost done. What this is, what these are is ordered pairs. What if you had 3 die? How could you write that? I don't think you can make this chart. You would just have 3 numbers, and they would be ordered. But you wouldn't have this times table looking type thing. And then there's a question, should I put commas between these? I don't know about that. I don't think I need those. Okay, did it. All right, let A be the event that the sum of the dice is 5. So that means when we add these 2 numbers together, we get the number 5. And what happens is we see a little pattern here. Here's 4, 1. 3, 2, 2, 3, 1, 4. Those are all pairs where the 2 numbers, the first and the second, add up to 5. And we see that there's a pattern that it forms a diagonal there. Notice that 4 as the first die and then 1 as the second is not the same as 1 the first and 4 the second. These are different, and we have to list both of those. So here I'll go ahead and write those out, but maybe we don't need to always, and then I made a mistake there. So because we can refer to the picture, and I already colored in part of the picture, so maybe that will do the job. But here we go. The probability of A is the number of elements in A divided by the number of elements in the sample space. Well, how many are in A? 1, 2, 3, 4. How many are in S? Well, there's 6 rows and 6 columns. 6 times 6 is 36. And that reduces to 1/9. What we can sort of, well, what we're going to see is that these are, this is the sum is 5, but if you notice, if you had the sum is 7, then there are more elements in there. That diagonal has more elements. This one asks us, what is the sum is 10? So for the sum is 10, I am going to switch over to a different color. 6 plus 4 is 10, 5 plus 5 is 10, and 4 plus 6 is 10. So B is equal to the set that has 6, 4, 5, 5, 4, 6, and the probability of the event B is the number of elements in B divided by number of elements in S, and that's 3 out of 36, which it turns out to be 112. Now, next one, let C be the event that both die show the same number. Color that in with another diagonal, but that diagonal goes in a different direction. All right. So let's list that. C is equal to the set 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. Okay, so probability of C is the number of elements in C divided by number of elements in S, which is 1, 2, 3, 4, 5, 6 out of 36. So that's 1/6. All right, now what's the probability of A union B? Well, the probability of A union B can be found by using the formula that probability A union B is given by the probability of A plus the probability of B minus intersection. What is intersection? Intersection is overlap. Intersection is overlap. So what is the overlap of A and B? What element is common to both A and B? Well, let's see, A has 6, 4, 5, 5, 4, 6. Oh, there's nothing. A and B are disjoint. So the probability of A intersection B is just equal to 0. So the probability of A union B is equal to probability of A plus probability of B. So if there is no intersection, then the probability of that intersection is 0. So we have probability of A plus probability of B. So that's equal to 4 over 36 plus 3 over 36. That's 7 over 36. Okay, did that one. How about probability B intersection C? B intersection C is the elements that are common to both B and C. Well, the one I see that's common to both B and C, for both, it's in both of them. That's what and means. What's in and B is this one element 5, 5. So the probability of B intersection C is the number of elements in B intersection C divided by the number of elements in S. And that's going to be, just because there's one element, is 1 out of 36. Now, to get probability of B intersection C, B union C, let's just remind ourselves what union means. Here's B and here's C. What's the union? And this is all sitting in the sample space S. So what's the union? The union is things that are in B, they're in C, and they're in both B and C. And we'll use the formula. The probability of B union C is probability of B plus probability of C. We could stop there if they're disjoint. Disjoint, remember, means that they have no elements in common, but they do. And so we're going to subtract the intersection, the elements they have in common. Now going from above, we see above from what we wrote before that probability B is 3 out of 36. So I'll write down 3 out of 36 for probability B. Probability C is 6 out of 36. All right, I'm just going to look at this one more time, make sure I get that right. Yes, 3 out of 36. Probability C is 6 out of 36, and then probability B intersection C is 1 out of 36. So all have a common denominator, so we have 36 in the denominator. 3 plus 6 minus 1, that makes 3 plus 6 is 9, minus 1, that makes 8 out of 36. Which, if you divide the numerator and denominator by 4, gives 2/9. All right, there you go. Goodbye.